Before watching the video, don't forget to subscribe to our channel by clicking the subscribe button below and clicking the bell icon to be notified whenever we publish a new video.
A DC shunt motor is a DC motor that has the field coil connected in shunt or parallel with the armature. A surprising operation of a DC shunt motor occurs when you decrease the current in the field coil and thus reduce the strength of the magnetic field. The motor armature will actually turn faster. This motor action is counterintuitive. You would expect that decreasing the current and thus producing less power would slow the motor down. To explain this phenomenon, let's take a closer look at what happens in a shunt motor circuit when the current is adjusted lower. In this diagram, we have an armature, which, as you know, is the part that rotates in the presence of a magnetic flux, a field coil that generates a magnetic field, and a controller to vary the field resistance, thus altering current flow and the strength of the magnetic field. Here we have a series of line diagrams to illustrate the relationships of the motor properties as a result of reducing current to the armature. When the field current is decreased, the counter-electromotive force, or CEMF, drops off dramatically. This sudden change results from a reduction in the EMF generated in the armature coils, which are turning within a less dense magnetic field. The less dense magnetic field is a result of the lowered field current flow. This also causes a spike in the voltage drop across the resistance of the armature. Because the total applied voltage is across the armature, any change in the drop across one part of the armature, either the CEMF or the voltage drop across the resistance of the armature coils, VRA, will be made up by an increase in the drop across the other component. Thus, if there is 100 volts applied and the CEMF is 80 volts, the drop across the resistance of the armature coils will be 20 volts. When the field current is reduced, the CEMF drops to 50 volts and the drop across the resistance of the armature coils, VRA, increases to 50 volts. Therefore, the total voltage is always maintained. Because the armature resistance RA is constant, as VRA changes the armature current, IA changes to compensate for the increase or decrease in the voltage drop. Thus, the current increase in the armature strengthens the magnetic field in the armature. A subsequent torque spike leads to a gradual increase in the speed. A new armature speed is attained after a reduced field current is established. The CEMF returns back to near the original levels as the armature spins faster in a reduced magnetic field. The voltage drop across the armature returns to near its previous level, with the current following a similar decrease. This happens when any of the parameters are changed, such as load and applied voltage, not just limited to field current changes.
Thanks for watching. If you like the video, give it a thumbs up and share it with your friends. For more tutorial and tips, subscribe the channel.